Fluid kinematics deals with the study of fluids in motion without considering the forces causing the motion. There are two primary approaches to analyze fluid motion. Lagrangian concept focuses on the behavior and path of an individual single distinct fluid particles over time. Eulerian concept focuses on a particular fixed section, volume, or spatial point in the flow field through which fluid particles pass. Uniform and non-uniform flow. If the velocity vector at all points in the flow field is completely identical at any given single instant of time, the flow is a uniform flow. If the velocity vector vary from one point to another at the same instant of time, the flow is non-uniform. dv by ds is equal to 0. This condition is strictly applicable only to the velocity vector across space. Laminar and turbulent flow. Laminar flow. Fluid particles move orderly in distinct layer or streamlines, smoothly sliding over adjacent layers without macroscopic mixing. Turbulent flow. Fluid particles exhibit random, chaotic, and erratic multi-directional movement leading to intense intermixing between adjacent fluid layers. Strict line. When a continuous traces of dye is injected into a liquid or smoke into a gas, a fixed special point, the resulting instantaneous curve that link all the fluid particles passing sequentially through the exact point is called streak line. Path line. A path line is the actual trajectory of the curve traced out by a single specific fluid particles over a period of during its actual journey through the flow. Streamline. A streamline is an imaginary line drawn within a flow field such as a tangent drawn at any special point along this curve perfectly aligned with the direction of the local fluid velocity vector at that point. By definition, there is absolutely no velocity component normal to a streamline. Consequently, flow can never cross a streamline boundary. Equation of a streamline. Since the tangents to a streamline matches the local velocity vector, the spatial component must be directly proportional to the directional velocity component. Dx by u is equal to dy by v is equal to d z by w. U, v, w components of instantaneous velocity in the x, y, z coordinate direction respectively. Continuity equations, conservation of mass. Based on the principle of conservation of mass, total mass entering a steady flow control volume equals to the total mass leaving it. Rho 1 A1 V1 is equal to rho 2 A2 V2, where rho density, a cross sectional area, and V mean flow velocity. For an incompressible fluid, the density remains completely constant. Rho 1 is equal to rho 2, modifying the simplified continuity equations to A1 V1 is equal to A2 V2. General continuity equations. The general differential form of the mass conservation principles in a 3D Cartesian coordinate space is given by dou rho by dou t plus dou rho u by dou x plus dou rho v by dou y plus dou rho w by dou z is equal to 0. For a steady flow, dou rho by dou t is equal to 0. Dou rho u by dou x plus dou rho v by dou y plus dou rho w by dou z is equal to 0. For a steady and incompressible flow, dou rho by dou t is equal to 0 and rho constant. Dou u by dou x plus dou v by dou y plus dou w by dou z is equal to 0. Total acceleration of a fluid particles. The total acceleration consists of two components: space dependent, convective, time dependent, temporal or local. The acceleration of a fluid along a particular direction consists of two parts: space dependent
convective, and time dependent, temporal or local. Understanding acceleration x directions, total acceleration in the x direction x is equal to u dou u by dou x v plus v dou u by dou y plus w dou u by dou z plus dou u by dou t. Last brackets, convective acceleration, temporal or local accelerations. Last one. Understanding acceleration y direction ay u dou v by dou x plus v dou v by dou y plus w dou v by dou z plus dou v by dou t. That is temporal or local acceleration and rest convective acceleration. Type of flow, convective acceleration or temporal or local acceleration. Steady and uniform, zero both steady and non-uniform exist. Other one zeros. Uniform, steady and uniform zero exist. Unsteady and non-uniform exist. Rotational components, vorticity and circulations. Rotational components represents the average angular velocity vector of two fluid lines elements. Expanding for the x direction components, omega is equal to half I j k dou by two half dou w by dou y minus dou. For an irrotational flow field, all rotational components are identically zero. Omega x is equal to omega y is equal to omega z is equal to zero. Vorticity and circulations. Vorticity measures local rotations and is twice the magnitude of the rotational component. Vorticity is equal to 2 into omega. Circulations, the line integral of the tangential velocity components around a completely closed curve. Circulation is equal to vorticity into cross-sectional area. In an irrotational flow, vorticity is absolutely zero at all points within rotational zones. So vorticity is non-zero. The real wall flow outside a boundary layer generally exhibits irrotational characteristics where fluids inside the boundary layer displays highly rotational characteristics due to the shear forces. Velocity potential functions a scalar function of space and time such that its negative partial derivative with respect to any direction yields the fluid velocity component along that specific direction u minus dou phi by dou x plus v minus dou phi by dou y omega minus dou phi by dou z. Fluid flow always occurs naturally in the direction of decreasing velocity potential. The velocity potential function phi exists only and exclusively for irrotational flows. Laplace equation dou square phi by dou x square plus dou square phi by dou y square is equal to 0. If a given phi satisfies the Laplace equations, it automatically fulfills continuity criteria, meaning the physical flow configuration is valid and possible. Stream functions. A scalar function defined exclusively for two-dimensional flows such that its partial derivative yields special fluid velocity components as follows: v is equal to psi by dou x dou eta u minus dou. Okay. If a stream functions exist in inherently satisfying the two-dimensional continuity equations, the underlying flow can be either a matricule rotational or irrotational. If the stream functions are explicitly satisfy the Laplace equation, it represents the irrotational flow case. The volume discharge per unit depth between any two streamlines is given directly. Q is equal to psi 1 minus psi 2. Cauchy Riemann equations and orthogonality. When both the functions exist for a two-dimensional irrotational flow of fluid, they are bound by Cauchy Riemann relations. Dou psi by dou x is equal to psi by dou y is equal to u. Thus, dou phi by dou y minus dou phi by dou y is equal to dou psi by dou x. Important property equipotential line phi constants and constant stream functions lies psi constant always intersect each other orthogonally perpendicularly at all points of intersections 90-degree orthogonal